This is the pre-lab lecture for experiment 9. A couple of things I want to emphasize here. This is actually the most lab-like what you would have done on campus if we were on campus. So this is what's called a dry lab. So got quite a bit to go over to get ready for this lab, but just like all the others, pre-lab data, post-lab, that's due all at one time. May 5th for the Tuesday lab, May 7th for the Thursday lab. Exam 1 was returned. Make sure and look over that because you can see your grade and you can see comments from me. So if you have questions, that'd be good to come to office hours and we can talk about that. You can also email me. I encourage you take advantage of the resources available. So you can use a discussion board, you can use on Canvas, or you can email your lab assistant. So the Tuesday, that's Jamie. Thursday, that's Kara. I will send out reminders about that at the end of the week. On Friday, the withdrawal date is May 8th, so if you got questions about this, let me know. And you can see we're cruising along. This week is experiment 9, next week's experiment 10. You have a total of 12 experiments, so not far off now. As I mentioned, this is a dry lab, so if you came in the lab room, we wouldn't have goggles, we wouldn't have lab coats, gloves. This is all work without chemicals, but it's really important work, okay? Especially if you're in my lecture, this is helping get ready for the exam 3. So I'll go through the steps of getting your electrons, drawing Lewis structures, then being able to distinguish between the electron or molecular geometry. I'll show you how you can use a simulation to get 3D structures. If we were in lab, you would have to build models to see the 3D structure. So you could still build models at home if you have marshmallows, toothpicks. If you had a model kit, you can do that. Or I have a simulation posted, you can work on that. We'll also look at polarity, if it's polar, non-polar, or if that doesn't apply. And then lastly, we'll talk about more complex structures and how it scales up for that. So let's take a look. I really want to emphasize these notes, okay? So first, there are hints on page 100. I really encourage you to look at these hints. Many times this happens in lab and students are frustrated, they're confused, and I say, hey, have you looked at this hint that tells you how the atoms are bonded? And they're like, where's the hints? Oh, there's the hints, page 100. Have that page open, refer back to that. When you're looking for polarity, okay, you have to have the electronegativity chart. You do not need to memorize those values, but you need to know how to use those values. So we'll talk about that, but page 150 is where you get those. The geometry chart, what are the shapes that we're talking about in this lab? So that's on page 151. Please note, for exams, you are required to know these shapes, okay? So it's not, this chart will not be provided to you. And as I mentioned before, you can use model kits, you can use simulations, but the idea is how do we visualize these molecules as 3D structures, not just as flat Lewis structures. So as I mentioned, I would require models, so you'd have to build models, you come up, we'd talk about the models, and then you'd be given some unknowns. So you will be given unknowns. So I really encourage you, it's worth doing all this work, looking at it, so then when you get to the unknowns, it goes really quick and straightforward, versus if you're not sure about all these examples, then the unknowns might be a little difficult. All right, so here's what we're gonna do. This is your experiment, and these are the steps, okay? So first, you're going to look at your formula and move left to right. So we need total valence electrons. So you look, this is Chapter 9 talked about all about electrons, and we got to electron configuration. The valence are the outside, so I'm adding up. That's 4 for carbon, 1 for hydrogen, and 7 for chlorine. There's 3 chlorines, so that's 26 valence electrons. Lewis structure, hydrogen will never be the central atom, so carbon is the central atom because it's farther left than chlorine, and because hydrogen won't be the central, so carbons are central. And we connect single bonds to the outside atoms. Then we look and see what our atoms are and realize that hydrogen only wants to be surrounded by 2 electrons. That's right there. Then we need to surround all these chlorines with 8. You can use dots to represent electrons, or you can see here with writing in this mouse, it's a little more difficult. And if I would do this same thing on the board as well, if you put a bar equals 2 electrons. So that's just a little easier to do. It's up to you how you want to do it. So this is the Lewis structure for this CHCl3. Now the electron geometry, basically the question is, how many electron regions do you have around the central atom? Okay, so we're constantly looking at the central atom, and in this case, we want to look and see that carbon has 1, 2, 3, 4 regions. Okay, so we go back to that chart on page 151 and we look, and that is a tetrahedral. Okay, so be really clear. Have students in the past that just write tet or tri, and it's not clear because there's several shapes that we're going to be talking about, and if you go to Chem 200, there's even more shapes that are similar. So really write out the whole thing. That's tetrahedral. Now the molecular geometry is asking about the molecule, so this is talking about atoms. Okay, so in this case, we have an atom at the end of this electron region. We have an atom here, and an atom here. So that's also tetrahedral because that's 4 atoms coming off and there's no lone pairs. So when you have lone pairs, that makes it a little more complicated, but there's examples that you can look at for that. Okay, the 3D structure now. Okay, so this is where we really want to draw what this molecule looks like. So I want to show you the simulation that I've left for you. And this simulation is called Chemistry FET. And what we're going to do is build our molecules. So when you come in, you're in this first tab of Make Molecules. I want you to select the Larger Molecules tab so you can see you have lots of atoms to work with. Our example was carbon, and we had hydrogen, and then we have 3 of these chlorines. Okay, so whoops, let's do carbon, hydrogen. This is a very similar structure here. So I did carbon, 2 hydrogens, 2 chlorines. That's what I have available here, and I'll show you how to get more atoms shortly. So build the structure and then hit 3D. Okay, so you can see this 3D, but this is still even a little confusing because this is the space filling model. So what you would have done in lab is build the ball and stick model, and so now you can see, and you can even rotate it. This is a tetrahedral shape. That's 1, 2, 3, 4 coming off of that carbon central atom. That's tetrahedral. You can rotate it. You can do a lot of things here. So this is a really nice simulation, fairly easy to use. So the problem here was didn't have enough atoms, so maybe you're looking also for other atoms. So just note that you can arrow over. You can see here there's more atoms. Look, there's what we could have done. Carbon, hydrogen, we needed 3 chlorines. So you can see it's wanting to put them all in 3D, and now you can see the shape, tetrahedral, of this. So you'll be asked to do with fluorine. There's also other atoms you keep going over, kit 6, phosphorus, oxygen. There's bromine that you need, kit 7. So this is a really good simulation to help with what we're doing, building molecules. All right, so we get back here. So now you've visualized to see what this looks like. And now we can fill out and draw what we think this looks like, okay? So for the 3D structure, we just want the atoms. Okay, we don't need lone pairs. You saw those lone pairs around chlorine. We don't need any of that. We just need a 3D structure. So I'm going to draw the best I can representing a 3D image of this molecule. And so you can see here, I'm going to give some spatial arrangement here, that hydrogen is coming out of the plane of the paper and that other chlorine is going behind the paper. So that is the best I can do right now of a tetrahedral arrangement. So you're not going to be graded on your artwork, but what's important is to be able to visualize what does this shape look like. So make sure your drawing represents a tetrahedral. Okay, so this last category is quite difficult. It's only one little box, it looks like, but you're determining, is this a polar molecule? Okay, so to do that, you need the electronegativity values, and those are for chlorine 3, and carbon is 2.5. Okay, so that gives us a difference of 0.5 for that bond. And then we had carbon, again, 2.5, and we have hydrogen, 2.1. That gives us the difference of 0.4. So the chart you can look at, you can see that 0.5 is a polar bond, and 0.4, it's kind of hard to see there, is a nonpolar bond. So what that means is we go back to the geometry over here, and we see that this is pulling in this direction, this is pulling in this direction, this is pulling in this direction, but hydrogen is not pulling down, okay, because that's a nonpolar bond. So overall then, this is a nonpolar molecule. Okay, we're looking to see if the pulls cancel out or if they don't cancel out. So, sorry, that does not cancel. I don't know if I said that right, but that is a polar molecule because that's pulling, doesn't cancel, so it's polar. If there was a chlorine here and it was pulling, it would be nonpolar, but in this case, this is a polar molecule. So that's the steps. That's what you need to go through. And again, with practice, you'll get a lot of this down. So then you can go through this a little more quicker and say there's 1 valence electron for hydrogen, 7 for fluorine, so that's HF, 8 electrons. And Lewis structure, hydrogen, that rule, it's a duet, so there's only 2, and here this is fluorine with 8. If it's just 2 atoms, this is going to be linear. There's no other arrangement for this, so both of these fall into this linear or doesn't apply, just two pieces. And of course, if you build this, then this would also just be in a line, 2 points connected like this. So no lone pairs needed. And then now the polarity, we probably want to make note that fluorine's the most electronegative. That's 4.0. And this hydrogen we saw up here was 2.1. So that's 1.9. And if it just has to be greater than 0.4, that means it's a polar bond. So we can draw in here and show it's pulling to the right, which means that's partial negative on fluorine, partial positive on hydrogen, and this is a polar molecule. Okay, the next one is ammonium, NH4+. So I wanted to put this one on to emphasize charge. So there's 5 valence electrons for nitrogen, 1 for each hydrogen, that's times 4. And then if we have a plus, remember, that means we lose an electron, okay? So I put -1, so that takes us to 8. So Lewis structure, again, hydrogens are terminal, so we put those on the outside. And what we do for polyatomic ions like this one, we draw the molecule, okay, so that shows the bonds. But remember, it's an ion, so we need to emphasize that. We bracket the whole thing and put the charge. So that's ammonium. So now the next category, remember, is electron regions. So again, we count 1, 2, 3, 4. So just like up here, that's tetrahedral. There's no lone pairs. That's tetrahedral. This, we build the molecule again in our simulation, and similarly, it would look like that shape. So get good practice drawing, trying to get some 3D representation, and that would look here. So for ions, the last three in your assignment are ions. So we're not determining polarity because they have a full charge. Remember, polar, nonpolar is referring to partial charges. Okay, is it unequal sharing? But this is a full transfer because that is a polyatomic ion. So this is emphasizing the what we see here with your assignment. You fill out all the categories: electrons, Lewis dot, the geometries, 3D, and polarity. So the polarity is a little complicated, so I just want to emphasize that a little bit more. And I got two examples here. Okay, I already said that carbon and hydrogen is a nonpolar bond, and carbon and nitrogen, on the other hand, is a polar bond. So nitrogen is 3.0, carbon is 2.5, so that means nitrogen is more electronegative, so it pulls in this direction. And sometimes you might see a notation with a positive on the partial positive, an arrow on the partial negative, or you'll see these symbols. So that means nitrogen's taking the electrons more, so we had more electron density region around the nitrogen and less around the carbon. So this would be a polar molecule because there's a pull to the right, nothing happening to the left. So if we go to this next one, carbon dioxide, carbon again is 2.5, and oxygen's 3.5, so it's definitely pulling. And take a look though, we have an oxygen on this side. So it's pulling this direction, and it's pulling this direction. And guess what? It's pulling the same, 1.0, 1.0. So overall, this is a nonpolar molecule. So the polarity, you have to take into account everything. The good Lewis structure, what's the shape, and then is it a polar bond? Is it not a polar bond? Does it cancel? So the keys here are, if you have a nonpolar bond, then you have a nonpolar molecule. Okay, that's the approach of your text. That's what we're doing here. If you have a polar bond, you can actually have a nonpolar molecule, as we saw here, because the pulls canceled. Or you can have polar bonds, polar molecule, so that's the molecule, this is bond, because it doesn't cancel. So the nitrogen is pulling to the right, doesn't cancel, that's polar, that's here. Cancels, that's nonpolar, that goes here. So start with the bonds. Are they polar or nonpolar? That's the difference in electronegativity of 0.4 is your category. So greater than 0.4, it's polar. And that's when we subtracted the electronegativities. And then move to the molecule. Okay, what's the shape? Do the poles cancel? That's nonpolar. So this was linear. Oxygen, as far away from each other as possible. This was also linear up here. So you can't just look at the shape and say, oh, a linear is nonpolar. Well, in this case, we saw a linear that's polar and a linear that's nonpolar. So that's very complex. Really encourage you to spend some time on that. Come to office hours. Let's talk about that. Lastly, what your unknowns are going to look like are a little more complex. Okay, so you're doing simple Lewis structures on your assignments, and then there's actually a few that are scaled up. And what I mean by is complex is the number of central atoms. Okay, so guess what? The rules are going to be the same. So there's no complex rules that are being added. We're just adding more central atoms. Okay, so what we would do here then is zoom in on one spot. So this is a central atom. You see this carbon is connected to several things. And if you look, this is carbon 1, we'll call it. Its electron regions are 1, 2, 3, 4. So its electron geometry is tetrahedral. And then we see that's 1, 2, 3, 4 atoms. Its molecular geometry is also tetrahedral. Okay, so we just did some tetrahedrals before. You got that? No problem. So this is carbon 1. Now let's take a look at carbon 2. This is a different shape, but this is 1 electron region, 2 electron regions, 3 electron regions. This is carbon 2. So 3 electron regions is trigonal planar. So again, I'm trying to emphasize not just trigonal, because there's also trigonal pyramidal. So I'm going to abbreviate for this writing, trigonal planar. And the molecular geometry, there are no lone pairs on this carbon, so it's also trigonal planar. Okay, so the molecular geometry and electron geometry are the same unless there are lone pairs, which we haven't done one of these yet. That takes us to oxygen here. And this is oxygen 1 because it is a central atom. This is a terminal, so we're not worried about oxygen. Okay, so a central means it's connected to more than one atom. Here, oxygen's only connected to one atom. So this is oxygen 1 central atom. So we take a look. Electron regions, that's 1, 2. I know we already counted that one, but now we're looking at it from the perspective of oxygen. That's 4. So that's tetrahedral. Okay, now we want the molecular geometry. So in this case, mentioned already, the molecular geometry is going to be different than the electron geometry, and that's where we refer to the geometry chart, page 151. And we look that there's only 2 atoms and there's 2 lone pairs. So this has a molecular geometry of bent. So you have lots of practice in this experiment 9. This helps get ready for the next lecture exam. So if you got questions, come see me during office hours.